Good evening, everyone. Thanks for joining this session today. My name is Ashpak Shaikh, and I'm a senior staff engineer and a GraphQL API steward at Intuit. I was born in Mumbai, India, and I came to US for my master's. And after my master's, I've been working at Intuit for about a decade now. For the past 5 years, I've been extensively working on GraphQL and mostly focusing on the backend side and the orchestration technologies. So a little bit of context about Intuit. If you see, you might have known Intuit for the apps that are listed at the top: TurboTax, Mint, Credit Karma, QuickBooks, and MailChimp. And some of these apps belong to the Intuit consumer group, namely TurboTax, Mint, and Credit Karma. And the other two apps are from the SBSec group, the small business group. So just giving you a quick overview of what is going to be in this session. We'll talk about the GraphQL Orchestrator problem, the history, architecture, the thoughts and learnings that led us to create our own orchestrator. We'll dive into the subgraph registration mechanism of that orchestrator, the schema composition use cases, authorization, and the REST adapters in detail. So let me start giving you a little bit context about how GraphQL was introduced to us and what is the orchestrator problem. So back in 2017, 2018 tax year, we were working on an idea of an app called Turbo, which would be collecting data from the tax ecosystem and the Mint ecosystem and showing it to the consumer and providing better financial picture by showing metrics like debt to income ratio, net worth, etc. Now, the tax supergraph, the tax data is very huge. It has like 50,000 fields. So the tax document is like in MBs of file. And similarly, the credit report is also huge. So we wanted to avoid like the overfetching problem. And that's why we chose GraphQL. But these two ecosystems are very disparate, and it has to be kind of merged together for the app to make a single GraphQL query and get all the benefits of GraphQL. So there was a need for an orchestrator in the consumer group ecosystem, and that's the problem that the orchestrator is solving for us. Now at this point, I would like to clarify the terminology that we use. We use the term GraphQL Orchestrator, but is equivalent to GraphQL Gateway or the supergraph. Similarly, for the subgraph, we use, I'll use the term subgraph, but I might also use the term provider interchangeably. So let's talk about what was the existing solution when we started. So back in 2017, like GraphQL was just becoming more popular, and we already had an orchestrator in the small business group called as the platform abstraction service. Now this orchestration service was actually existing even before GraphQL was a thing and GraphQL became popular. This orchestrator actually orchestrated across REST services using a prepared query specification, and it kind of did a dynamic query model, but GraphQL was not the primary spec that it worked on. The schema authoring was done in YAML, and the orchestrator used to talk to the subgraphs using a prepared query specification. Now, as GraphQL became matured and the need for GraphQL started, this orchestrator was modified and actually it actually started catering GraphQL requests as well. So this was not natively built for GraphQL. The credit service that I was just talking about was already registered with this orchestrator, and this orchestrator was already performing scale at the SBSec groups. We had almost like 15, 17 subgraphs, REST subgraphs and GraphQL subgraphs registered with this orchestrator. So I belong from the tax world, and from a tax perspective, our job was to register a tax subgraph to this orchestrator for the Turbo app to actually get the credit and tax data together. Now, to give you a high-level process of how PAS worked and what was the process of schema authoring and registration, there was a central Git repo, like I mentioned, which had schema and YAML files. So as a developer of a tax subgraph, I have to come in, create a PR to this central Git repo, and then that once the PR is merged after proper approvals, jar file or a Java archive file will be created, and that archive now needs to be taken down as a dependency in my Spring service or the Java service, and that's how I will write the resolvers in that service. It's not the traditional GraphQL model where you actually start with SDL first, because the way the PaaS was evolved, right? In addition to the schema jar, there was also a SDK, a PaaS SDK that used to be, that we need to add as a dependency, which actually helped wiring the resolvers. That's not it. The third step was the subgraph actually consuming this jar, and we actually registering manually with the supergraph that this type belonged to this service. The routing configuration I had to done manually. So these are the 3 steps where we actually had to go through to register the tax subgraph with the PaaS orchestrator. Now, you'll see that this is very inefficient and unoptimized, and there were a lot of challenges with PaaS. So like you see, the schema updates, even for like a small field change, we had to actually make a PR, consume the jar in the subgraph and the supergraph both. So there were a few challenges. Then we tried creating our own schema repository so that with the goal to actually expedite the process, but it didn't work. The SDK version incompatibility caused an issue where the subgraph and the supergraph needs to be actually on the same version. Then triaging issues with the execution actually required expertise. We actually had a big incident where the subgraph and the supergraph were not in the compatible version, and that actually caused the issue. Now, because it was not built for GraphQL, the PaaS ecosystem was not up to date with the latest GraphQL specification. You could not do unions interface with the YAML specification, and even for the runtime part, it was difficult to upgrade the GraphQL Java library on an ongoing basis. So very difficult to take upgrades. Yeah, while we were doing that, and we actually went with that PaaS tax subgraph in the PaaS ecosystem, and we were actually live for a year. While we were doing that, there was another service. I wouldn't call it an orchestrator. There was another service in the TurboTax live world where they were creating a distributed kind of model, distributed in terms of Git repo, not in terms of the deployment. A distributed model where the subgraphs or a part of the schema would be in the GitHub repository, which will be working off of, different teams will be working on that Git repository in an independent manner. It will be bundled in a jar format, and then that would be integrated in the GraphQL gateway, and the gateway will get deployed. Now, I don't like to call this gateway because it's just a monolith where modules come together as a POM dependency and deploy. So you can see that this had a problem where you can quickly get into a problem where it will be difficult to manage the versioning of the different modules in this service, right? But this service actually was a crucial service because it actually meant that the subgraph teams or the developers are happy with coding schemas in the GraphQL format and like native GraphQL, writing native GraphQL resolvers. So now from the learnings from these 2 orchestrators, we decided to come up with our own orchestrator. We surfaced the issues with the consumer group leadership and the architect community, and got a mission team approved to work on our own orchestrator. The goal was very modest. Let's just combine the TurboTax live GraphQL service and the PaaS, the consumer group PaaS schema into one unified graph, and then project it to the consumers. But we had the vision of this GraphQL orchestrator will be the single endpoint data API for all things data fetching in the consumer group. Right? So with the learnings and the takeaways that we had from our experience with the GraphQL world, we established 2 fundamental principles. First principles, one is on the execution side, and on the other one is on the registration side. On the execution side, we decided that we'll just follow GraphQL spec as the standard format for schema authoring, and even for the communication between the subgraph and the supergraph. For registration, we had failed, or we didn't find the process very efficient in the other two orchestrator ecosystems. So it was very important to do loose coupling between the subgraph and the supergraph, so that they can follow their own deployment life cycle and they can actually work independently. So at this point, before starting diving deep into the orchestrator, I'll just share some numbers. For this the orchestrator, the consumer group, we have 54 subgraphs registered with 150 plus clients calling this orchestrator, 18 REST adapters. I'll talk about it in detail in the next sections. And there are 60 plus ODZ clients. I have a section for ODZ also. The orchestrator only added 6 milliseconds overhead on the execution, and we reached a max TPS of 5K almost every tax season in the past 4 years. Now, let's start with the subgraph registration. We have a very simple registration mechanism where we created a registration library for the subgraphs to consume. What this library does is, at startup, it will call the orchestrator's register endpoint. It will send the files to the orchestrator, the schema files and the routing files for validation. The orchestrator will run the validation against the schema that is live, and then it will tell the subgraph whether your schema is valid or not. If valid, it will post it on S3, which we use for persistence. Now the orchestrator is also listening on S3, so that at any point or from any pipeline S3 is changed, the orchestrator will automatically refresh its schema. I've highlighted this in detail in the sequence diagram, where the orchestrator starts up, it takes the file schema persisted on S3. Now the subgraph comes in, validates the schema. On success, the subgraph will actually proceed with startup. On failure, the subgraph actually fails the startup. Now you'll be wondering that failing a startup for a subgraph might be too severe or drastic a measure to take, but this actually helped us catch a lot of issues early on in the life cycle of the schema development, because failing startup means it also failed for local development when the developer is actually working on the schema and making schema updates. So any schema composition issues while the developer is working, we were able to catch it, they were able to fix it, and we were able to, we hardly saw any issues when the service is actually deployed on the actual environment. Most of the issues were caught in the local development, right? And whenever the orchestrator detects a schema change, like I mentioned, it will refresh its master schema, and that's how it will just keep up to date with the latest schema. So this actually architecture helps us with decoupling the subgraph and the orchestrator, and they can have their independent software lifecycle, right? The other thing that I wanted to mention was the GraphQL registration files. The registration files are like the schema files, of course, what your API looks like, and the routing configuration files. It's a very simple routing configuration file with just the namespace, type, and the endpoint that the orchestrator is supposed to call for this section of the schema, right? The key takeaways that we had from our registration mechanism was introspection is awesome, but it did not work for the way we did registration, because we did it on startup, and the validation or the startup is supposed to fail when this subgraph schema is not valid, right? So it is causing a chicken and egg problem, like what will you validate if the service is not up? So we were not able to actually proceed with the supergraph making an introspection call to actually get the schema. So that's why we went with the subgraph telling the schema files, giving the schema files to the orchestrator to validate. The other learning was, do not mix the schema and the configuration, routing configuration, unless necessary. We actually did something like, we actually had some kind of configuration like type renaming and field renaming configuration in the configuration file, but that didn't scale much because we were trying to like not add unnecessary directives to the schema or to the orchestrator ecosystem. So the configuration was a good file to keep all of that, but it didn't, I think keeping it more closer to the schema actually has its advantage, right? Like I mentioned, early validation, local validation reduces the registration issues significantly. We were hardly able to see any registration issues while the app is being subgraphs are deployed, maybe once or twice in 6 months, separating the live traffic from the subgraph registration. Now, if you see in the previous architecture that the orchestrator has the register endpoint, right? So separating, the orchestrator also has a GraphQL endpoint. So you'll be wondering the registration validation or it's actually high memory consuming task. But the way we were able to go across this was keeping separate swim laning for the orchestrator, for the register calls, and for the GraphQL calls. The reason we had to actually do the validation in the orchestrator was because the orchestrator has the latest version of the schema that is live. So the validation is just very real, right? It's actually validating against the latest version of the schema. The other thing I want to point out, right, like there needs to be a balance between how long you go with self-service and how much schema governance you can do. So one example that I would like to share on this is type name conflicts. Like we didn't have a lot of schema conflicts. We went for self-service to start with, like making sure that the subgraphs are able to develop individually and there's not a lot of blockers for the subgraph. Now, you might have learned a lot about type conflicts, strategies for type conflicts, but I would like to point out a different problem where the tax subgraph in this example has a type profile, but it also has an existing client, right? But the credit subgraph is already registered to the orchestrator using the type profile, right? So when the tax subgraph comes to register, it automatically detects a type conflict, but it cannot change or rename the type to tax profile or something else because it has existing clients using the type in the fragment, right? So what we provided them with was a way to rename their type only when they register with the orchestrator. This means that they can keep the type profile in the tax subgraph, but when they actually register with the orchestrator will replace all references of profile with tax profile. And at the execution time, the orchestrator has enough metadata to determine that, okay, when I am actually using tax profile with this tax subgraph, I need to strip out the tax or use the original type to actually make the queries to tax. So this wouldn't have been a case if we would have started with schema governance from the beginning itself, because at that point you can actually enforce everyone to have a standard type and not actually have same types in the different service, right? So that brings me to like the schema composition use cases that we had. We started growing, the number of subgraphs started growing. It was easier when the subgraphs are actually very independent and not actually have relationship between them. But as the number grew, there began requests coming on terms of like, I want to organize a schema so that all my subgraphs within the same domain have a common parent. Or there are dependencies between subgraph which needs to be represented in the supergraph so that the client makes a single query across these dependencies, right? Client always wanted to make a single query, so they came up with use cases like I'm actually calling the orchestrator, but I'm making two different queries in a sequential manner. So would it be possible for you to stitch to these two subgraphs in a way that I only make a single query? Now, while we were figuring out these issues, there were a lot of literature. I think this was around the time 2018, 2019 into the development. There were a lot of literature and diverse spec for distributed GraphQL schema. There was stitching, federation was just coming up, but not a lot of Java libraries which supported this. So we came up with we implemented some of the schema composition in our own way. One such feature was top-level merge. Top-level merge is very standard. Tax and credit service, it actually merges both of them together, like we were seeing the Turbo example, at the query level itself, right? Now, let's take an example of a recursive merge algorithm. So we have a user subgraph which has a user, which provides the user personal info. Now, there's a tax subgraph which provides details about the user, but it has the financial info and gives out tax information. And we have a credit subgraph which is also in the finance domain, and it gives out the credit information. Now, if you see, there are things that are common in these subgraphs. The user type is, if you traverse from the query type, the user type is common. It has personal info, finance, and the finance type is common. It has tax and credit in a different subgraphs, right? So the final graph actually, the recursive algorithm actually starts from the query node. It finds the common elements. It keeps on stitching, goes and next to the next level and goes to the next level until it finds out different things. And ultimately, it comes creates this unified schema so that the client can actually call this in a single query, but you also get the output as organized unified schema, right? So the second use case is remote type extension. It's the first one was starting from the query and actually going deeper. But the second one is arbitrary. I have a tax info type in my tax subgraph, but that only gives me the tax ID and the year. It does not give me anything, any kind of tax data. The tax data is coming from the tax document subgraph, which is working, which takes a query, which is the tax document query. It takes in the ID, the tax ID, and the year. So how can the client get the actual document in a single query? So for that, we came up with this resolver directive where the tax subgraph can keep an extension file. They don't have to load the extension file in their runtime, but they can pass this extension file to the orchestrator, and they can say that, okay, I need to add the tax document field in my tax info type, and for that, the resolver is not myself, but the resolver is a different field in the actual compose supergraph, which we'll need to pass in the arguments ID and take in the tax ID from my tax info type and pass it, and the argument year is same as year. So you can keep different argument names and actually stitch them together. Now the final graph, unified graph, looks like where the tax info type has the tax document type, and this is what is visible to the client. So the client makes a single query, it just merge together in one. So the next type was, the next type of schema composition that we did was, now Apollo started becoming very popular. There are subgraphs that started using Apollo. So we wanted to actually support the Apollo federation also in this orchestrator. So with the same example, tax info type, we need to add the tax document subgraph, but with the Apollo spec. So the Apollo spec looks like we have to use, define the tax info as entity. We need to use the extend keyword and the external keyword so that it can understand that someone else is extending. The only difference here is in this case, both the subgraphs need to decorate the schema with the directives. And I think the name or the key needs to be common. You can't have a different name for the keys or the arguments in the previous slide. But the result is the same. We support the same thing with the Apollo Federation spec as well. The client can make a single query and get all the data together. Now, we had a unique use case where we need to actually do federation plus resolver, because if you remember, the PaaS subgraph in the PaaS ecosystem also now need to participate in the the consumer orchestrator ecosystem. So with this example, let's say there is a PaaS subgraph actually providing tax filing information. The tax filing information needs to be part of the tax document type. So for that, we use resolver. So we have this actual use case where we have stitching with federation, and the next level of stitching happens with the resolver directive. The unified schema is very standard. The tax document, tax info has tax document has a tax filing, and the client can make all the three services, subgraphs together in the single query. Now with all of these schema composition use cases, all of these use cases support batching, meaning the number of queries that goes out of the orchestrator for a given subgraph will always be one. We've implemented data loader concept in the orchestrator so that we perform that optimization in the orchestrator level. Now, talking about authorization, we started, as the number of clients started to grow, we had different profiles of clients, real user versus offline job processing, user with lower access level, user, we need to check for consent for before giving access. There are third-party apps which are actually interested in calling the orchestrator and getting data from the consumer. Now, the GraphQL is a single endpoint model, so traditional REST models will not work, or whatever has the REST API is quite mature in this ecosystem. We need a different solution for the authorization. So we went with central authorization enforcement, because most of these authorization use cases are to be done by gateway, and traditionally at Intuit, the API gateway does all of this enforcement. So this is how the architecture of the authorization looks like basically. We have an instrumentation library that we created using the GraphQL Java library. The job of that library is to look at the rules and redact the query. So before the query execution, it will take the main query, apply some rules, I will talk about the rules shortly, and then redact the query, and then the orchestrator executes it. The benefit that we get from this is, in this example, if the credit service query is redacted, we don't call the credit service at all, right? So network optimization there. Now the schema authoring part, we used this model that we actually learned from PaaS, where we have a central repo. The subgraph, the client actually creates request or creates request access to a particular part of the super graph with a query syntax, and it has its own identification, like client ID and the type of the ticket. Now the GitHub PR is validated against the schema. We have built plugins to validate the schema. And then the subgraph developer, or the actual subgraph owner, the domain owner, approves the PR. The PR gets merged, it is uploaded to S3. Now the orchestrator, like it's listening to events for schema, it also listens to the event for the authorization. So without any restart anywhere, the OTZ rules are updated. The new clients can now, we can enforce authorization pretty dynamically. So that was about the authorization. Now the orchestrator ecosystem actually grew quite huge, and there were cases where clients became very spoiled and they wanted data from REST services now. And REST services, the subgraph teams are not actually ready to adopt the GraphQL interface because of resource constraint. They are in maintenance mode, they were not ready. So we came up with the concept of declarative REST adapters, where the orchestration can actually project the data that it receives from the REST endpoints into to match the GraphQL schema. So I'll share about that in a little bit. This adapter support is also part of the registration library, so they can keep that, and it's all dynamic. And we also created an adapter pipeline for services who are not in development mode. So client can themselves come create a PR, adapter PR, and then get the benefit of GraphQL by themselves. So the PR or the files looks very simple. The adapter is very declarative, and we have a DSL to represent the REST adapter. The DSL route, because in the consumer group uses a lot of these DSL concepts, and this is one of the DSL that was already being used. So we use the same DSL to represent the REST service. The only additional file in addition to the other registration file is the flow file, where you will specify your REST service contract on how to make this, what the REST call you need to make for that particular pet category. And we also support cross-linking, like if you see the pet category type in this example is actually being highlighted, and if you command click on the pet category in the flow file, it will take you to the GraphQL file. So that cross-linking and validation that comes free for DSLs and declarative content is already built in. So let me summarize what we just learned so far. This is a simplified architecture, and this is actually a true architecture that we have in production. It's very, as you can see, it's very simple. There's a lot of moving components. We use S3 for persistence. We have adapter for REST services, and then we have authorization enforced at the orchestrator. So this simplified orchestrator actually helped us to scale to the numbers that I just shared, 54 subgraphs and 150 clients, and it has worked since 4 tax season for us. I want to close out with sharing our open source GraphQL repository. We have open sourced all the components that are shared today. The orchestration library, the authorization library, REST adapter library, and we use GraphQL Java heavily to to build all of these because our orchestrator is written in Java, the ecosystem is Java. So please go through the GitHub, create issues, get involved, and give us feedback on the repositories. And that's about it. Thank you. These are my details. You can reach out to me in any of the channels, and if you have any questions, I'm ready to take any questions. Yeah. Okay. So the question is basically, what does self-service actually mean in what I was mentioning in the slides, right? So self-service means that the subgraph is independent and self-serve to actually register with the orchestrator. There's no blocker for them. We have documentation, we have libraries, we have checklists that they can actually go by themselves and register with the orchestrator, right? The other side to it is once we make it fully automated and for the fully self-serve for the subgraph developers, the schema governance becomes difficult because they can create the schema the way they want, and there's no governance or eyesight over what's happening, right? But we are trying to solve that with a centralized governance process in addition to automated self-serving. And if you might have seen the talk from Jared and Suresh, I think yesterday, he talks about the governance and the the API JEDI program that we are coming up with to actually manage centralized governance. Yeah. Yeah. So let me rephrase that question. So were there any pros and cons for redacting the query, and were there any consideration for partial errors? Is that right? Yeah, error at all. So the way it works today, we redact the query and give out partial errors because we didn't want, because they don't have access to the other parts of the subgraph, we didn't want to make the whole query invalid. Also, it needs to be incremental, right? So if a client with a low level access comes with a field 1, 2, 3, right? They have access to those fields. Now they need the access to field 4. So what happens is they need to incrementally actually register those queries, and we don't want to break the old query. So they can make the query change before and then apply the ODZ policy. That's also fine, right? So we always wanted to go with incremental approach. On the redaction part, the biggest benefit that we saw, and I mentioned it, was not having to call the subgraph unnecessarily. Because when the query is redacted, it means that the whole query might belong to one particular subgraph and you're saving 1 or 2 network calls. Right? Yeah. Yes, yes. Yes, so the tools were basically the registration library, right? One of the biggest one. It takes care of validation in itself. It will take care of if there's any composable issues, it will catch and notify the developer. And it will also point them to links to how to fix it. They can read documentation on, okay, there's a type conflict, you need to go via this route or add the rename directive, right? So that basically that was there. Then there were Git repositories, like I mentioned, created where the subgraphs and the clients collaborate by themselves for ODZ rules. They can come create adapters by themselves. The orchestrator is just listening on S3. Anything changes on the S3 for adapters, new subgraph schemas, or ODZ rules, the orchestrator will just pick it up. Yeah, it may happen like as part of the subgraph development or as part of the GitHub pipeline for ODZ and adapter registries. Sorry? Oh, so we don't have it catching at the ID level, but we are working on when you will have an extension in the ID where it will, when you are in the GraphQL schema development phase, you can actually call API behind the scenes and it will validate your schema. Currently, it's only at startup, and we also have developed a Maven plugin, which is widely used, where they actually can just include that plugin in that form. It'll read your schema and validate it at build time. Right. Cool. Any other questions? Cool. Thank you for your time, guys.